we got over the weekend, all over the place. We went to Northridge and Milton.
All right, the Valley's my stomping grounds here. All right, okay. Well, happy Friday, halfway through the quarter, and we'll take a look. And thanks for tuning in. This today's lectures are little, I don't know, just like little odds, bits and ends. So anyway, we'll just a couple of topics thrown in here today. All right, I got 2 sets of slides. One's all handwritten. These ones are like half handwritten. So we're in chapter 2 in the textbook. I know it's taken so long just to get through 2 chapters. But we'd had like a neural networks detour, so that's my justification. There's a section that talks about variability in predictions. So remember, we have created a model, a probabilistic model for kind of generating our values, and we said the mean, the new values have a mean of W hat transpose X new. So this is kind of our prediction, and we recognize that our estimates of W hat are subject to the random noise that was in the data that we used to train it, right? So if you could be developing a model and you collected data and your friend collected data and you're developing basically the same model, but because your data has random noise and your friend's data has random noise, your W hats are going to be different. And therefore, if you get a new value, an X new, and we said, hey, make a prediction for the number of, X equal to 50 or something, depending on what your friend's observations were and their W hat, and what your observations and your W hat is, there's going to be variation between what you predict and what your friend predicts, right? And that's what this is getting at, okay? This is getting at how much variation is there. And the derivation of this is in the textbook, and I'll just leave it to you as an exercise to kind of look in the textbook on these pages to kind of go through it. But basically they say, all right, what is the expected value of your predictions? And it's just W hat transpose X new. And then you using basically what you learned in like 100B, how do you calculate the variance of a random variable? And you go through a bunch of steps and you get kind of this quantity, sigma squared, X new transpose, X transpose X inverse, X new, X transpose X. These X are the values of X that were used to determine your W hat, whereas X new is obviously the new X that's going in. And sigma squared is kind of the inherent variation in your observations. So if you're thinking about, if you think about during your training, you have kind of like noise, right? Random noise, and that's what makes your observations and your W hat different from your friend's observations and their W hat. That's part of sigma squared. And so the variance of your new your new observations, are subject to that. Okay, so the values of Y themselves do not factor into the variation. It's all kind of there is variation in the Y values, but that can just be summarized with a single variance number. Whereas the individual values of Y themselves don't matter. You just need kind of the overall, what is the variance or variation there. There is an interesting thing that happens between kind of what is your X new and what is your X transpose X. And so I have a couple example, I guess like X matrices and X new, and it has some kind of surprising or maybe surprising, but also like intuitive results. So I guess, intuitive if you think about it. So we're going to say, let's say we, in our data, when we kind of observed the y values, and again, the actual y values don't really matter. We're just going to say there's like the variance sigma squared is just going to be 1 to keep it simple. And we can say, okay, when we trained our model, we had an observation at x equal to 1, an observation at x equal to 2. We have a column of 1s for the intercept, and then basically values of x here, right? So I have a column of 1s for the intercept. Column. This column is 1, 2, 99, and 100. So I have an observation when x was 1, x is 2, and the way over here when x is 99 and x is 100. And then I said, okay, what if I get a new value, and I want to say, okay, how much variation do I expect if I'm trying to make a prediction at x equal to 50, right? And again, we say, okay, well, you know what? My friend might have had different random observations. I might have, well, anyway, if we do this, the x new versus, x transpose x inverse times x new, we get a small, well, you'll see, this is a relatively small number, 0.25, okay? And this reflects that if our prediction is right in between kind of like the range of x going from 1 to 100, and we're kind of in between there here at 50, there's not a ton of room for error. So sorry, excuse my handwriting here, but basically we're saying, okay, we have an observation at x equal to 1, x equal to 2, x equal to 99, and x equal to 100. And then I have these other dots, these red dots, to kind of indicate like, yeah, there's random noise. So, maybe we got some values as high as here or as low as here, as high as here, as low as here. And these different lines indicate kind of different linear fits, right? Depending on the random values that ended up in your data set, what are the prediction lines that you could have gotten, right? So if you happen to get large values, your y values ended up being large for 1 and 2 and small for 99 and 100, you might get a shallower slope. If your values were like, your y values were low for 1 and 2 and high for 99 and 100, your slope might be a little bit steeper. But again, not the overall, like how much of an impact does it have on x new, which is 50, right in the middle? There's not a ton of variation here, okay? And that's reflected in this small number here, okay? On the other hand, what if you have observations, if your X matrix, you have observations at 1, 2, 3, and 4, and then we break, we commit one of the statistical cardinal sins of extrapolation, and we do, say, make a prediction at x equal to 100, right? We know this is a terrible idea. We should never do this. But even if we were to assume that the linear relationship were to hold, and it's actually true or something, we can see, look at the variation here, okay? So if I do, x transpose x inverse, and then I do t, x new transpose times, x transpose x inverse times x new, my variation here is 1,901, okay? Versus, again, back here, it was 0.25. Here it's 1,901, okay? And what's going on, all right, so this is, my next slide is trying to illustrate what's happening, is that we have the values 1, 2, 3, and 4, and again, there's random noise, and based on what we see in these 1, 2, 3, and 4, we could get, like a variety of different fitted lines. And then if you kind of extrapolate those, right, you get some values. You might end up with the yellow line for the fit values you see, and you could end up way out here, right? It's also possible that just because of the random noise in your data, you end up with this purple line as your fit. And if you extrapolate all the way out to x new equal to 100, you can see, now, and we say make a prediction for what t would be when x is 100. You can see, there's a whole lot of variation, right? So, again, just imagine you collected data for x equal to 1, x equal to 2, x equal to 3, x equal to 4, and you fit make a model based on that. Your friend also collects random data at the same things. And then you're both given this task, make a prediction when x equals 100. And then, both again, because of your random noise and your friend's random noise, your predictions could be very, very different, okay? Whereas, again, going back a few slides, even if your values were different, we wouldn't expect there to be a huge amount of variation here, okay? And then kind of the same kind of thing happens if you go in the other direction, if your new observations. So, it's interesting that somehow in this, X transpose X inverse, X new, even if I have 1, 2, 3, 4, and I do this, I get these really big values. And just even in the opposite direction, if my X values were, say, 97, 98, 99, 100, and I'm saying make a prediction for when X is 0, we also get a huge amount of variation here as well, okay? I didn't draw a picture, but it's basically the reverse of this. However, just throwing in, if we throw in a point, so here I have a value at 0, 50, 100, and 101, throwing that in there, throwing an observation x equal to 50 into the training data, and then I say, okay, make a prediction at x equal to 50, we get, again, a small amount of variance, okay? And even if I remove that data point, so here's, so if I have this, even if I remove it, okay, the amount of kind of variance doesn't change a whole lot, okay? It's just, we go from 0.27 to 0.37, yeah, it gets bigger, but, removing this data point, this 50, doesn't make a huge difference here, okay? So here I'm saying, I have an observation at 50, and again, the fitted lines, not a whole lot of variation, so we don't have a ton of variation. Here, I get rid of the observation at 50, and I'm still asking how much variation do I have, and the answer is still not a ton, okay? Still not very much, okay? What's interesting though is, what if you go from a linear model to a quadratic model, okay? A linear model to a quadratic model. So your x observations, will have an intercept term, an x, and an x squared term. And here I just put in 0, 50, 100, 101, and I have 0 squared, 50 squared, 100 squared, 101 squared, okay? So we have these four observations. And I say, okay, well, make a prediction for when x is 50, okay? So it's basically 1, 50, and 50 squared. We plug that in, we get variance around 1. I gotta look up, I keep remembering I got view quiz answers and stuff. Okay, so we have this, okay? Watch what happens if I remove this one line, okay? If I remove this from the quadratic model. Okay, so if I remove that, my variance gets way, way, way bigger, right? And so, so this is strange, right? Because for the linear thing, going from having these 4 lines, 0, 50, 100, 101, and then removing it, 0, 100, 101, didn't make a huge difference, okay? But here, I've got a quadratic model. I got 0, 50, 100, 101, and I've got this variance. Removing that one entry here suddenly makes my variance way bigger, okay? And so there's kind of this fascinating thing that happens, when we have the X transpose X inverse and we're multiplying it by basically X new on each of these sides. The illustration here maybe will reveal what's happening, okay, is, when we're fitting quadratic models, right? So we're fitting quadratic models, and we can go from 0, 50, 100, 101, and if we have an observation at 50 and it's like locked in here, wherever it is, again, the actual y values don't really matter, it's just like we have some location and some variance in these things. You can imagine these lines kind of being fit like this, right? if you have these observations, 0, 100, 101, depending on the actual values at 0, 100, and 101, you can imagine your quadratic fit end up being, kind of like this green line or ending up like this purple line, right? Because technically when you have 3 points and you say fit a quadratic model, like you can fit those 3 points like perfectly, okay? And just depending on kind of the amount of, like whether you happen to get a high value for 100 and a low value for 101, or a low value for 100 or a high value for 101, that's gonna like flip where he goes. And so when we say, hey, what is the variation around the new observation at x equal to 50, there's going to be a huge amount there, okay? And actually, if we do x new closer to, say, 100 or closer to, say, 0, that's actually, the amount of variation there is going to be a lot less, right? So there is kind of this interplay between these things. Let me go ahead and give you your first view quiz answer. I got to look this up, though. Friday. Okay, first answer is D. D as in dog. D as in dog is our first view quiz answer. Okay. So anyway, that is kind of this, just like just some examples of this concept of variation or variability in predictions. And there is, when we're fitting some kind of linear model, there is an interplay between what x observations you have and what your new x value, where you're asking to make a prediction for x new, and kind of also like how complicated your model is. And if you have an overly complicated model, you could end up with some situation like this where when it comes to making the predictions, there's actually having a more complicated model actually becomes like a little bit of a liability when it comes to like reducing the amount of variation in your predictions and things like that, because higher order models certainly offer more flexibility. Okay, again, just encourage you to do some of your textbook reading regarding that stuff. Okay, we are going to flip over, and here I've got some handwritten notes on the multivariate normal distribution. And I don't know, you might have seen this in 100B already, multivariate normal. Is that where you guys cover this? Okay, well, so this is an old hat, but we kind of take this into account for some of our future models. So we'll do like a classifier, a Bayes classifier that uses like a multivariate normal distribution, and things like that. So next week we'll start looking at some like classification models and things, and this plays a role in it. So I just kind of want to review it, and if it's review for you, let's see, then it's review. Okay. So first I start off with just the univariate normal distribution for one random variable, okay? And we would say x comes from a normal with mean mu and variance sigma squared, okay? And then we have, the density is 1 over root 2 pi sigma squared, e to the negative x minus mu squared, divided by 2 sigma squared, okay? And, and I should probably link to this 3 blue 1 brown video talking about the normal distribution, how pi makes an appearance, like where did this pi come from? It's pretty great, because I never thought about it, and it was just like, oh, okay, yeah, we just throw that in there. It just has to integrate to 1, but it's like, oh yeah, how does that? Okay, it's pretty amazing how e and pi are related, right? Okay. Now, when we're dealing with the multivariate normal, okay, our x values the x values are these vectors, okay? And so, we can have a d-dimensional vector. A lot of times we, just to like plot things, d is only 2, but you could have a 3-dimensional, 4-dimensional, something like that. It's just harder to imagine. And in that case, we'd say x, the vector x comes from a normal distribution with mean vector mu, okay? And our variance is this variance matrix sigma, okay? And sigma is going to be a d by d positive definite variance matrix. And the density for this thing is 1 over square root 2 pi raised to the d, determinant of the matrix sigma, e to the -1/2 x minus mu transpose sigma inverse x minus mu, okay? And it feels a little bit scary, but there are actually a lot of kind of similarities between the univariate and the multivariate one. Because if you think about x minus mu squared, that's a lot like x minus mu transpose x minus mu, right? As far as, vectors go, okay? And then 1 over sigma squared is kind of like multiplying by the inverse of the sigma matrix, okay? So here we're dividing by, and then there's also the -1/2, that's still there. And then here we're dividing by root sigma squared here, and then we're throwing in the determinant of sigma, and the determinant is kind of this weird, it's not that weird, but it's a little bit weird, right? It's equal to the area or the volume of like if you think of your sigma matrix, you get these vectors in your sigma matrix, and you get the maybe it cuts out a parallelogram, and it's the determinant is the area of that thing. Or if it's higher dimensional, you get this 3-dimensional or higher dimensional solid parallel pipette, I guess is what they call it, and you're taking the volume of that. And you just have to remember that this constant, it's a constant with respect to kind of your x. This constant in the front, its purpose is so that the area or the volume or whatever it is integrates to 1. Okay, so this is what we're looking at. If we have a simple example where our sigma matrix is the identity matrix, okay, then the whole thing boils down to a product of 3 independent normal distributions, which makes sense because this variance matrix represents down the diagonal is the variance of each individual thing, and then the other values are the covariances. And so here, if I'm saying, mu, each value has a mean of 0, right? x1, x2, x3 has means 0, 0, and 0, and then my variance matrix is a bunch of 1s. Then x transpose I inverse is I, right? So x transpose sigma inverse x, this boils down to just x1 squared plus x2 squared plus x3 squared, okay? The determinant of the identity is 1, okay? And so I have 1 over root 2 pi to the third, and here is e to this. And, because I have a sum of x1 squared, x2 squared, and x3 squared that I can factor out into the product of e to the negative x1 squared, e to the negative x2 squared, e to the negative x3 squared. And so this is exactly equal to the PDF of a standard normal, PDF of a standard normal, PDF of a standard normal. So it's just 3 independent standard normal distributions and their total product together. And this is generalized to if you're in the multivariate normal distribution, if you have 0 covariance between some of the elements, then it just becomes the product of those elements, okay? So here is, just more generalized. If we have all zeros in our, for the off-diagonal elements, so if our sigma matrix is just a diagonal matrix with just the variances sigma 1 squared, sigma 2 squared, up through sigma d squared, not necessarily 1, but any other kind of value, right, then your determinant is the product of all of these sigma I squareds, and then the inverse of a diagonal matrix is just 1 over your diagonals, okay? And so, if you expand this out, you're going to get basically the inside the E, the exp part, you're going to have a bunch of sums, which will then could be factored out into, x minus mu1 squared over sigma 1 squared, and so on and so forth. So if you have a diagonal matrix, then the multivariate normal is just the product of a whole bunch of univariate normal distributions, okay? And that makes sense, right? Because you don't have to worry about any covariance, right? So covariance would indicate that as if you have, x1 and x2, if they're independent, then when x1 is big, x2 can be big or small, or like highly positive or highly negative, or whatever it is, right? Could span anything. If there's let's say if there's high positive covariance, then when x1 is above average, we expect x2 to be above average. When x1 is below average, we expect x2 to be below average. But if they're all kind of independent, all of our off-diagonal elements are 0, indicating no covariance, then we can just treat everything as independent. And when things are independent, their probabilities are just products. Okay, this is like the fact that things can be factored out into products is like we keep falling back on that in statistics. Okay, let's see. All right, so here I have a 3-dimensional vector, x1, x2, and x3. And so now I have some covariance and things like that. And so all to say, here are just some kind of properties of the multivariate normal distribution, is that, if you have some mean vector, here I put in 1, -1, 2, and now I have a sigma matrix where I do have some covariance between, x1 and x2, and, x1 and x3, and x2 and x3, and things like that, okay? And remember, your sigma matrix has to be a diagonal thing. That's going to be the result if you use the definition of covariance here. The marginal distributions will just be like if you were to just look at only the x1 variable, or only the x2 variable, or only the x3 variable, they individually, they are all normal distributions, okay? So x1 alone is going to be have a mean of 1 and a variance of 4. x2 will have a mean of -1 and a variance of 1. And x3 will have a mean of 2 and a variance of 9, okay? And so, if you just reduce it to just that one dimension, you have normal distributions. And then if you look at, say, any 2 variables, you'll have the covariance that appears in here. So x1 and x2, if we looked at, what is the covariance between x1 and x2, we will find that there's covariance. Covariance of 2, okay? What's the covariance between x1 and x3? These are actually orthogonal. There's no covariance between them because we have a 0. And then x2 and x3, there is covariance, and we have negative covariance here, okay? So it's hard for me to picture this because it's in 3 dimensions, but we do have some kind of covariance and also independence between these things, and it's possible to have that kind of structure there. All right, let me give you your second view quiz answer, which is the letter C. C as in cat. C as in cat is our second view quiz answer. Okay, and then also subsets of this thing also will be the multivariate normal. So if you look at just one variable, you have the normal. But then if you look at a subset of, say, 2 out of the 3 of these things, that will also be a multivariate normal. And so if I were to kind of, we're generating like 3 values at a time, okay? And if I were to just kind of subset that row into just kind of 2, here I'll just do x1 and x3, then it's basically just, I have the mean of this multivariate will be kind of the mean of x1 and the mean of x3. And then the variance of those things will just be kind of the corresponding sub-elements of our variance covariance matrix, okay? And so in this case, I would take, the 4 and the 0 and the 9, okay? And so in this case, this is what I would end up having, and x1 and x3 happen to be independent, but I could also, get this, I could look at x1 and x2, or x2 and x3, right? I'm trying to think, what's an example of in real life where you have covariance between x1 and x2, you have covariance between x2 and x3, but you have independence between x1 and x3. Okay, I got it. Or wait, no. Is this? Wait, no. Independent. Covariance. Oh no, maybe they are all have covariance. Wait. Okay, wait. No, sorry. I got to rethink this. X1, X2, and X3. I'm just trying to think what's an example where you have covariance between two of these things, but then independence between. I gotta think of it. There's covariance there. There's covariance there. All right. Well. I'll think of something. Some conditionally independent I can think of. Yeah, well, okay. Let me come back to that later. Okay. All right. Properties of kind of combinations of some of these things, okay? So we could define, so let's say X comes from this multivariate normal distribution, okay? So X is coming from a normal with mean mu, vector mu, and variance matrix sigma. And then we have Y. Y is, you take some C matrix, okay, and you're going to multiply it by X, right? So you have this kind of this non-singular matrix, and we're going to say, okay, what is Y? So Y is going to be kind of like a linear combination of these X terms, okay? What is the well then Y itself? If you are taking if C represents kind of a linear combination of the kind of the elements in X, then Y itself will also come from a multivariate normal distribution, okay? And the mean of Y's multivariate normal distribution will be the product of C times mu, and we'll have this variance matrix C sigma C transpose. So we're going to say X is comes from a multivariate normal. Actually, it's just two independent normals. So X comes, has mean 1 and variance 1, and X2 has mean 2 and variance 3, but there's no covariance between X1 and X2, all right? And we're going to say Y is going to be, a linear combination of these things, and so we'll just keep it simple. We'll say Y is going to be the first element of Y is going to be X1 plus X2, and the second element of Y will be X1 minus X2, okay? And so if you think about, all right, so X1 normal right? X2 is normal, and they're independent. But now we're going to have, all right, is there covariance between the values of getting x1 plus x2 and x1 minus x2, right? And so this is like a little bit of a puzzle, but yeah, there ends up being covariance between these things. Even if the elements x1 and x2 themselves are independent, when you say, hey, we're going to add these two things together and take the difference between these two things, then you end up getting some covariance. So let's see. So to represent what is x1 plus x2, we can say the first element will first row of C will be 1 and 1, and then the difference x1 minus x2 will be 1 and minus 1, right? And so we can see if I do C times x, right? If x is x1 and x2, we can see that indeed we're going to get x1 plus x2 on the top, and then on the bottom we'll get x1 minus x2, and that's exactly what we want for y. And so what is the mean of y? Well, this makes intuitive sense. The mean of the top will be 1 and 2. We add those together, so we have an expected value of 3 for the mean of y1. And then the difference will be -1. We have an expected value of -1, 1 minus 2 for the mean of y2. And then the covariance, or the variance, okay? Well, we add the variances, okay, and we get 4 and 4 down the diagonal, and I think that makes sense, right? Because x1 can go, have this variance of 1, and x2 has this variance of 3, and so you end up getting a variance of 4 there. But yeah, you get some negative covariance between y1 and y3. Did I say x? What I meant to say y, right? So you have a variance of 4 for y1, variance of 4 for y3, or y2, and then you get negative covariance between y1 and y2, okay? And that's found by doing the product of C times your sigma matrix times C transpose, which in this case looks like this. Here our C matrix is a square, but it doesn't have to be, right? Because you could have, your X matrix could be, you could be generating 3 values, and then the resulting Y could be like a linear combination of those 3 into like 2 values or something like that, okay? I guess this is just a little derivation of this, all right? So the expected value, you say expected value of Y is the expected value of C times X, and we can see, okay, oh yeah, this is going to be C times the expected value of X, which is just mu, and then if you think about what is the variance of Y, then it's what Y is minus the expected value of Y times that, and then you take out all of these things. Well, anyway, you can read through it, and you get basically this result, right? Because you can basically take the C's out. This thing ends up being the expected value of this thing is the exact definition of the variance of X, which we said was sigma, and we say, oh yeah, C sigma C transpose. So that's a little bit of a derivation there. Okay, I guess that's it. So we'll go ahead and end here. Let me give you your last view quiz answer, which is the letter E. E as in elephant. And so I couldn't think of an answer here. I thought I had something, but it's not, and it's kind of all right. Let me jot down. Let me get my ideas here. All right. So we have variable x1 will be I don't know, Adam's commute time. Variable x2 will be Bob's commute, and variable x3 is the bus. I don't know, the bus time. But then maybe this is not quite right, okay? So we're gonna say Adam rides the bus and then walks to work. And then Bob rides the bus, rides same bus, and walks the rest to work. Does this work? Okay, so and then the bus drives, right? Okay, so these are not there. So if the bus takes a long time, then Adam, if the bus ride is above average, then Adam's total commute is above average. And then if the bus ride is above average, then Bob, so there's covariance between all of these things, right? Bob's total commute is above average. But kind of, if you factor in the bus ride, if you subtract off the bus ride, then Adam's time to work and Bob's time to work would be independent, right? If that's conditional. Yeah, so that's conditional independence. But so I'm trying to think what would be I feel like there's something independent. Okay, well, so that would be conditionally independent. All right, well, bonus points if you can give me a reasonable example. Yeah.
So, this is maybe more complicated than that, but like coastline oil reserves and per capita GDP.
Oil reserves, per capita GDP.
Yeah, and like coastline length or
coastline what?
Length or like ratio
Length.
to area.
Oh, okay, so coastline length. So we're looking at like countries?
Right.
Okay.
So then,
So if a nation has above average coastline, then we'll have above average oil reserves.
or no, per capita GDP is
Okay, then per capita GDP is above average. Okay. And if and we're expecting coastline
to be independent of oil.
to be independent of oil reserves. Okay. All right, there we go. And if a nation has above average oil reserves, then per capita GDP is also above average. Okay. All right, there we go. So coastline and GDP, positive correlation. Oil reserves and GDP, positive correlation. Coastline and, okay, there we go. All right, great. We'll give you some bonus points there. Okay, so this would be an example of that. All right, this one's conditional independence over there. All right, okay, great. I'll keep that in mind. Okay, all right. Well, anyway, we'll call it a day here. Have a great weekend, and we will see you back on Monday. All 10 of you.